Okay, welcome to Thermochemistry Part 2. I want to add and expand on a couple of things we did in the last video. The first one is that when you're writing equations, we can write what are called thermochemical equations where you list the heat in the equation. So as an example, what I might do is I might write an equation like this. I might say, hey, 2H2, let me put this on here, 2H2 plus O2 will produce 2H2O plus some amount of energy. In this case, I believe it's 483.6 kilojoules. Okay, so notice I've listed the energy in here as a product. So this is coming out. Now you should always list the physical states, and I'm not sure I left myself enough room here, but these are gases. The water would come out at a high temperature, so it will actually be steam, so it will be a gas. But notice the energy is listed right in the equation. So when I list the energy as a product, this is exothermic because this heat is coming out. Now I could also use the delta H notation and write this as 2H2O, and we'll list that as a gas, plus O2, listed as a gas, producing 2H2O, which, as I said, is a gas. And then what I can do is over on the side, I can write delta H equal to, and I can give the number. In this case, it would be negative 483.6, and that being kilojoules. So notice what's happened here is that I've actually separated the heat from the equation, but since it's negative, I know it's exothermic. So when you include it in the equation, it's always positive, but if you include it as a product, of course, it's exothermic. If you write it as the delta H notation, it would be exothermic, but it would be negative is the key thing. Now, I could, of course, write this reaction backwards, and I could do 2H2O plus 83.6 kilojoules, producing, did an arrow there, producing 2H2, which is a gas, plus O2, which is a gas. Now notice here I've listed it on this side of the equation, so now it's endothermic. I'm having to put the energy in, and again, I could write this also, oh, I'm seeing a mistake here. This should be an H2. Let me fix that. I apologize. Okay, so it's 2H2 plus O2 producing 2H2O. Now let me go back to the equation I'm on here. 2H2O plus 483.6 kilojoules produces 2H2 plus O2. If I were to do this in the delta H notation, it's the same equation. I do 2H2O, arrow. I'm sorry, I keep forgetting these states here. This is a gas. This is a gas. Arrow producing 2H2 plus O2, and again, these are gases. And then if I do the delta H on the side, it's going to be positive 483.6 kilojoules. So I apologize if my writing's a little sloppy, but please just, the details on this equation aren't as important as you recognize that with an exothermic reaction, my heat is listed as a product if I write a thermochemical equation and include it right in the equation. If I do it in the delta H where it's off on the side, oh boy, that was pretty bad. It would be, here we go, let me do this. There we go. It would be negative, so that either listed positively as a product or in the negative as a delta H notation. If I reverse the equation and want to include the energy right in the equation, it's now listed as a reactant. Or if I do the delta H, it would be off on the side, and again, now it is going to be positive. So these are just a couple of ways of writing the equations. Now, what I'd like to do is reference this equation a little bit, and in general, I kind of introduced this in the previous screen. I said that, listen, if my reactants are here and my products are here, and I would get some sort of an energy diagram. Notice my products have less energy than my reactants, so energy was released, and this is going to be exothermic. If I have a reaction diagram that looks like this, here are my reactants, here are my products. Again, it's going to go up, it's going to absorb energy, and of course this would be endothermic. So these are just a couple of different ways to present this sort of thing. Now, when we get to this sort of diagram, the reaction coordinate diagram, what we're showing is the energy going in the reaction, and we're showing our through time what happens and what changes occur. A couple of things you should be familiar with. We always start with our reactants and we have our products here. Now if you compare just the reactants to the products, you get the overall energy released from the reaction Okay, so of course this is my enthalpy and this is my delta H. My products are lower in energy, so I'd get a negative number, so this is going to be an exothermic reaction. Now, what is this stuff up here? Well, there's a theory, it's called collision theory, and basically it describes how for molecules to react, in this case this is glucose and oxygen, they need to come into contact with one another. In collision theory, there's several things that will affect that and improve the likelihood of it occurring. Some things that might include the orientation of the molecules. If it's kind of a complex interaction, they may need to be oriented in the correct way. Anything that will increase the number of collisions will increase your reaction rate. So things like increasing the temperature will increase the number of collisions, which can increase the rate. Increasing the pressure sometimes will increase the number of collisions, which will increase the reaction rate. Anything that will increase the force of those collisions sometimes will help as well, and that would be things like heating it up, because again, when you heat things up, when you input heat, the molecules move faster. Their temperature goes up, but again, their temperature is rising because their kinetic energy is going up, and because of that, they're going to have more collisions and they're going to have greater force, which means you're going to have more of them that have what is known as the activation energy, and that's what I want to discuss here. What happens is if two things are going to react. They have to react with enough energy to kind of overcome their existing bonds and to form new bonds. As these things collide and come together, they form kind of a transitional state called the activated complex. And that is kind of a transitional state. It is not the reactants, it's not the products, it's that middle state where the things have collided, some bonds have broken, some new ones have formed, but we really aren't on either side of this yet. We haven't produced this, we haven't produced this. Well, that takes a little bit of energy. Certain reactions require a lot of energy. I mean, they don't react very easily, and these two molecules really need to slam into one another with a decent amount of energy for this activated complex to occur. But this energy is known as the activation energy, and sometimes that's abbreviated E sub A. That is the activation energy, and that is the difference between your reactants and your peak here, your activated complex. If I'm coming in the reverse reaction, I also have an activation energy, and the activation energy for the reverse reaction, of course, is the difference between my products. And so this would be for the reverse reaction, going backwards. So if I want my products, my CO2 and my H2O, they're going to have to collide with this amount of energy for them to come back. And that would imply that you can have reversible reactions, which of course you can do. Now, one thing, and this emphasizes what enzymes will do, this is the basic reaction. The red line here is your base reaction. If I add an enzyme, what an enzyme does is it somehow, and there are different mechanisms by which this can occur, but it basically lowers the activation energy. It somehow helps these guys come together, and maybe they need less energy, maybe it helps them orient more effectively, but it will somehow allow this reaction to occur more easily. And the general term here, and I'm kind of, is a catalyst. Okay. Enzymes are a form of catalyst. They're biological. It's a protein that helps a reaction occur. So while this says enzyme, a catalyst is a more general term, and there are a lot of reactions, but what a catalyst does is it allows this reaction to occur more easily by lowering the activation energy. So notice that my activation energy with the enzyme or the catalyst is much, much lower. So what that means is more of my collisions will be effective and I will get more product. So anything I can do to lower this activation energy generally speeds up the reaction because it allows the reaction to go more quickly, speeds it up, and by speeding it up, you get more product, and so the reaction will produce more product. Okay, so that concludes thermochemistry part 2. I hope this was helpful to you. And we're going to move on next to, I believe, bond energies will be the next video.